Okay, so good morning everyone. So welcome to the morning session of today. So the first session we have three speakers here. Our first speaker is Professor Qianxiao Li from the National University of Singapore. Today he will give us his talk on dynamic system approach to the different welcome.
So thanks very much, first of all, for inviting me to come here and give this talk. I'm very happy to be here. So today I'm going to discuss some recent work I've done with my collaborators on a kind of connecting deep learning on one hand and dynamical systems, calculus variations on the other. And hopefully, it gives us some insight into some key aspects of deep learning, for example, the role of function composition. So this is joint work with my colleagues both in Singapore and also in Peking University and Princeton University. So we start with some simple background and motivation. So the topic that we're primarily interested in is that of supervised learning. So it's about making predictions. So we have a data set consisting of inputs x and labels or outputs y. And we assume there's some oracle function that maps the input to the output. For simplicity, you can think of it as a deterministic function, but it can also be something with noise. So in this case, this f star is a oracle classifier that classifies the cats and dog images into the corresponding labels. Okay. So the overarching goal of supervised learning is to learn, or if you want, approximate f star using information from this data set. Okay. So the very first step to doing so is to define some sort of hypothesis space. So this is a space of relationships you can probably represent on a computer easily, or optimize easily, and so your goal is to pick some function out of it. Okay, so the simplest one for linear models, either for regression classification, consists of functions of linear combinations on basis functions. Okay, so this can be called some sort of feature maps. And for classification, of course, you need to match the output, to labels. So sometimes binary classification you get a sign, but otherwise it's very similar. On the other hand, you have this sort of nonlinear models of shallow neural network is one example. So here you have some, kind of a special basis function of a affine transformation followed by some nonlinear activation. So of course the form is the same as the any basis function, but the difference here is that the basis function here is not fixed a priori. You didn't choose it, but you learn it from the data. Okay, so it depends on the data. So in some sense, it's a bit like a nonlinear transformation. And of course, sigma is the activation function. So there's a lot of choices. There's a ReLU, a very popular one, and also tanh, sigmoid, etc. So what's different in deep neural nets is basically trying to recursively apply this transformation of a shallow neural network. So a deep network can be thought of as a composition of many layers of shallow network. Okay? So it's one of the primary distinguishing features of deep learning when you compare it to the other kinds of models. So after defining the space, of course, you can ask, okay, what's next? We want to find some function in the space so as to fit our data, right? So this is often done using empirical risk minimization. So what we do is we define some sort of distance notion on the output space, and our goal is to minimize the distance between our predicted output, which is f. Okay, this is a function that we chose from a hypothesis space. And the target, okay, the actual output, which is the output of the oracle function. Okay, you can only have access to the oracle in this form. And minimizing this gives us some approximate effect. Okay? But really, what we really want to solve, even regarded as a learning problem, is not entirely an optimization problem, because what we really want to solve is the following, which is the expected or population risk minimization, where instead of just making this sort of model prediction work on these samples here given to you, you want it to work also on unseen samples. Let's say it's new samples drawn from the distribution, and this distribution mu star is unknown to you. Okay, it characterizes the input-output joint distribution. So very often this is what we want to solve, and this is what we can solve because we need data from it. And the distance between these two is usually not zero. And the gap between them is the study of generalization. Okay. So to summarize, I think you can roughly give three paradigms when it comes to supervised learning. The very first problem you can ask in supervised learning is that of approximation. So basically, you ask how big is your hypothesis space? Does it include this oracle function, or is it close to the oracle function? How far is it away from it? So this is a problem of approximation, and in fact, this has been discussed a long time ago in approximation theory for harmonic analysis and things. But doing this is not good enough because even if you know this is very close, how do you find this function, right? So then there comes the problem of optimization. So starting from any classifier or regressor, a random guess, say, and then how do you use the information from the data set to arrive somewhere hopefully close to what you want? And of course, as I said before, this is non-zero because the data set is finite. So you have the problem of generalization. Okay, so approximation, optimization, generalization are three sort of large, rough classes of problems you can think about when it comes to supervised learning. Maybe not just for supervised learning, but in this case, it's a rough classification. Okay, so what is new in deep learning? Because everything we said before applies to everything, including linear regression. Okay, so what's new in deep learning is really the role of composition. So the hypothesis space is very complex, and we need to understand what is the role of this repeated application of some method on your hypothesis space. Okay, so there's a lot of mathematics developed whether it comes to approximation and also optimization, backpropagation, and things like that. But the problem is that we really lack a simple framework where you can really explicitly consider the role of composition easily. And instead of doing a case-by-case analysis of different architectures in neural networks, we can ask, is there something that we study in mathematics that composition really plays a vital role? And can we try to understand, in that case, what is the approximation properties and optimization properties, etc.? So it turns out there is one area, and it's a pretty large area, it's the study of dynamical systems. So when you study the evolution of certain equation, let's say Navier-Stokes or something, you're really composing a lot of mappings together, and they produce very, very complicated behavior. So the viewpoint that we're trying to propose here is really to use the flow maps of certain dynamical systems as a hypothesis space for supervised learning. You can think of deep learning as one special examples of this, where the dynamical system is formed by repeated composition of shallow neural networks. This is a discrete time dynamical system. Okay? But what we want to do here is to pick the simplest possible such dynamical system where we know a lot about, from the mathematical point of view. And that is dynamical systems modeled by ordinary differential equations. Okay, so we know a lot about ordinary differential equations. So this is what we're going to consider in this talk. So we have a dynamical system modeled by ODE, where the forcing function depends on some parameter every time that you can pick. So you can think of this as a caricature of neural networks, deep neural nets, where each theta t is the weights at the tth layer. Okay, and this induces a hypothesis space of flow maps. Okay, so this hypothesis space contains all the flow maps where you use z, the input z, is treated as the initial condition of this dynamical system, and as you evolve it through time, finally you take some simple function to match the output dimension. So here, this hypothesis space consists of flowing with the dynamical system and then applying a simple kind of last layer, whether it's a classification layer or regression layer, and form your hypothesis space. Okay. So to try to illustrate what is the role of this kind of flow and why it would help us in building good machine learning models, I'm going to give a quick demonstration of a binary classifier. So here, we're trying to classify this group of points in 3 dimensions. And you can see clearly that there's no hyperplane that cuts through them to separate them. So what's going to happen is that we're going to try to use the hypothesis space of dynamical systems and try to train a flow so that under the flow, after you apply the flow to all those points, this problem becomes much simpler. And you can probably separate a linear function. So this is what happens when you train this. And this NN layer is really T. Okay, so this is the time. And you can see that as the time increases, the flow separates these 2 sets. And now you can apply a very simple function G to separate them. So in this case, the hypothesis space of this flow map is really useful in dealing with this kind of problems. Okay.
So you, by flow, you are thinking more intuitively the flow of every observed points, or in that sense?
Yeah. So the flow, it has an actual sort of mathematically speaking.
You apply to each point?
Yeah. So you apply the same flow to every single point, viewing each point there as the initial condition. Okay, so each point is flowing with the same dynamical system but different initial condition. And if you design the dynamical system well, in this case it's not so hard, that at the end you'll be able to separate it easily. Okay, so this is still the underlying principle.
So are you saying that each layer, in the neural network sense, each layer has the same weight?
Oh, no. So you see, like, this theta t depends on the layer. Okay, so for each theta t, you pick it from the same space, or I mean, maybe like a n-dimensional Euclidean space or something, but the weight is different for every layer. Yeah.
Also, another question is, for such simple problem, if you use the neural networks and use traditional training, you probably only need 2 or 3 layers,
Yeah,
right?
right.
But for this, you need like 100 layers or something?
I mean, I don't need it, but I'm just trying to illustrate that for this simple example, this flow can also, do what you expect it to do. Of course, that's not a minimal model. The minimal model is probably much simpler than this. Yeah. But you will see that the role of composition is important later on when I show some mathematical results that really depends on this composition.
So your hypothesis space also change.
Well, here I can fix the terminal time. If I fix the terminal time, then this hypothesis space is really driven by this parameter set. Okay, but of course you can consider unions later on. I will of different length flows. Then that the hypothesis space changes with big T.
So the dimension also change with time.
The dimension, embedding space is changing.
You mean the dimension of this set?
Right.
Okay.
We have the embedding space. Different layer has different dimension.
Yes.
So you treat it as a flow automatically.
Yes. I think that will be a much more systematic way to do it in more generality. But here I'm just going to consider a simple ODE in a simple space. Yeah, that's very good. So I'll continue. So as just a quick remark that there is some connection between this and a very successful application in deep learning called residual neural networks. The residual net is basically like a usual deep learning deep neural net, except that you add some residual connection to each layer, so this identity mapping. And the quick observation is that if you apply some Euler discretization to our flow-based hypothesis space, you will get something formally similar to a residual network, provided this term is small, so that you can put a delta t here. There is some experimental evidence to show that this is indeed the case for very deep neurons. Okay, so this is just a quick remark saying that there's a connection between this and very good neural network architectures. Okay, so there's a bunch of work on dynamical systems and approach using ODEs and try to analyze and also try to understand different aspects of deep learning. For example, network architectures, optimization algorithms, theoretical analysis, applications, etc., etc. So I'll go through all of them just to show you that this is quite a fruitful direction to look at deep learning. So in this talk, I'm mostly interested in the mathematical basis underlying this approach. So I'm interested in all the 3 questions of approximation, optimization, and generalization. And you can see that each of these problems actually related quite a lot with very established fields of mathematics, but with some slight differences. So I will only have time to talk about maybe a little bit of optimization and also approximation. Okay, so on optimization. You can think of the sort of expected risk minimization problem here over flow maps as this kind of optimization problem, where we're trying to minimize some functional that depends on the entire path of controls or of weights, because now they are continuous in time, and you want to minimize the expected distance between the output and label. So this term is clear. And I'm going to consider a slightly more general case where there's some regularizer that you can apply at every layer. So when I say layer, it means time. Okay? And of course, you have this ODE flow. So if you are familiar with optimal control and calculus of variations, you will see that this is very similar to a calculus of variations problem. You're trying to minimize over a curve, right, of some function. But the key difference here is this part. The initial condition of this differential equation is actually distributed according to some distribution. And the terminal sort of loss also depends on this distribution. So in some sense, we call it, this is a mean field control problem, in the sense that your controls, when I say controls, I mean your theta, the weights that you learn, must be shared with the entire population of input-output pairs. They can't just work for one pair of input-outputs. Okay? It has to be the same for entire population. Okay? So this is a different kind of problem. And of course, the first mathematical question we can ask is, if I pose some variational problem like this, can I derive some necessary conditions for optimality that hopefully depends on this kind of evolution and composition, and not just saying that, okay, the gradient of this function equals 0 and that's it, right? And hopefully we can also discuss some sufficient conditions. So I'll talk about this in greater detail. So what is the necessary condition? It just means that if I give you a solution, theta star, of the problem, can you tell me what must this satisfy? Okay. So why we care about necessary conditions is often in establishing a necessary condition, you can help us identify some algorithm to try to find that. Gradient descent, you can think of that as inspired by the condition, gradient is equal to 0 at the optimum. So here we can do some very similar things. Okay. So what we can prove is the following. So we define a Hamiltonian function h that depends both on our forcing dynamics, every kind of activation every layer, and also the regularizer. And this is kind of a little bit like a Legendre transformation. You've seen this in physics. So given this Hamiltonian function, we know that we have the following result, which says that this theta star, which is a solution of our learning problem, okay, must maximize this Hamiltonian pointwise in time. Okay, so it is the global maximum of this Hamiltonian in not unique, but it is the global maximum of this Hamiltonian function at every single t, every single layer. And the x star and p star, these two, actually it satisfies some Hamiltonian dynamics. So if this is the first time you're seeing this, this is actually a generalization of the classical Pontryagin maximum principle in calculus of variations. If the first time you're seeing it, it's difficult to parse, but it's okay. I will tell you what is the main, the takeaways from this. The very first thing is that in deriving this necessary condition of optimality, I did not make reference to derivatives with respect to theta at all. Okay, so in some sense, it's quite a general condition. And secondly, the parameter set theta, where you can pick your weights at every layer, is highly general. So no matter what theta is, okay, this is going to hold. Okay.
Sorry, what is the regularizer you were talking about here?
Okay, so this is the regularizer I can apply to every layer. So you can think if let's say theta t is the weights at every layer, I can say I can apply L2 regularization. So this just corresponds to R being theta squared, and I can integrate that contributes a lot.
But in most of this neural network training, they don't necessarily explicitly have a regularizer.
Yeah,
so
you can have it or you can don't have it. I mean, you can set R to be 0, everything else, I mean, the condition still holds. I'm just saying that you actually can do a little bit more by having the regularizer. Yeah. Okay. So the parameter set is very general. So I don't need it to say contain an open neighborhood where you can do some first order kind of perturbation. This neighborhood can this set can be even finite. There's a finite number of ways that you can pick. This will still hold. So it's quite general. And the maximization condition, as I said, is pointwise in time. Okay, so this thing is for each t, and they do not depend on any other values at other times, as long as you know x star and p star. Okay, so if you can solve this system, then the maximization is decoupled in time, which means that the maximization problem is much cheaper than the original calculus of variations problem. Okay, if it's not cheaper, then you probably haven't done much. Okay, but this is true. So each of this property actually leads to some algorithms. Okay, so the first one is no derivative. You actually can show that you can derive training algorithms by just not relying on gradient descent at all. Okay, and it actually sort of generalizes backpropagation. The maximum principle, in some sense, you can think of it as a generalization of this backpropagation idea of calculating gradients using forward and backward flows. And moreover, because the parameter set is very general, you can also derive training algorithms for special kind of networks, like quantized networks. Quantized networks are those where your weights are not just any value, but you constrain it to be, say, +1 or -1. Okay, sometimes for a lot of applications, it's very useful because you can store the weights in a much more compact form. So in that case, doing naive gradient descent is not going to work, because if you do gradient descent, you're no longer at the +1 or -1. But in this case, the maximum principle still holds, so you can use that to derive some algorithm. Okay, so we have done that in this paper. And of course, the last point is that you can come up with parallel training algorithms because the maximization condition actually is decoupled. Okay, so there's some work in called EMPIRICAL on this. Okay, so turns out that you can also derive some sufficient conditions. I'll skip this, but in the end, you will get some sort of Hamilton-Jacobi PDE that characterizes sufficient conditions for that problem, much like the dynamic programming approach using Bellman's principle. But it was some slight complications because you need to go to infinite vector space. Other than that, it's straightforward. Okay, so 5 minutes. Okay, so I will briefly discuss the problem of approximation. Okay. So in some sense, this is a more basic problem because I haven't really told you like how big this flow map space really is, right? What kind of functions can we approximate? Okay, so this is our hypothesis of flow maps, and here we can try to consider even bigger space where say we can allow any number of layers, so any terminal time. We take the union of all this and then ask how big is this H infinity? Okay. So there's some relatable. I'll just skip it. Let's just go through our results. So we can ask this already in one dimension, and it's not so trivial. So we can take X to be a one-dimensional compact set, and Y is R. And in this case, we don't need the final function because our input and output dimension is the same. Okay, so we can just take the output function to be identical. So the following observation is immediate. It's saying that any function in our hypothesis space must be continuous and increasing. Why is it increasing? Because if you look at the flow maps, right? So this is my initial condition. If they are arranged in this order, x, x prime, x double prime, at any time, these trajectories, the values must also be arranged in the same way. Because if not, let's say in this case, you will have trajectories crossing, right? So we know that this ODE is satisfied at every single point. So if this trajectory is crossed, then if you start from this point, you will lose uniqueness to the solution of ODE. Okay, so they must be increasing. Okay, so this is a well-known result in ordinary differential equations literature. But what's interesting is the reverse. So what we can show is that if we consider ReLU networks, okay, you can show that any continuous increasing function can actually be approximated using this dynamical system. So it is not very big, but it's big enough for all continuous and increasing functions. So of course the corollary is that if you're allowed to go one dimensional higher, you can then approximate any continuous function of boundary variation because you can always decompose it into an increasing part and a decreasing part. Okay, and then you can approximate those at the same time. And what's really interesting from this approach is you can ask the further question, I believe is a more important question, is what are sufficient conditions you can place on this class of mappings, basically the architecture of the neural network, so that it can indeed approximate any continuous increasing function. Okay, so here we propose, we can show the following result, which says that if this function, so big F, is all the different forcings you can choose every layer, if it satisfies, if it is symmetric and translation invariant, so if H is in F, then minus H is in F, and then any translations in F, and if the convex hull of this set contains a function that looks like something like this. So there is an interval at which it is 0, and everything else is not 0. So as long as the convex hull contains this, then you can show that you can approximate any increasing continuous function. Okay, so of course ReLU satisfies this because you don't even need to take the convex hull, but all the sigmoid and tangent you can take the convex hull and get this. Okay, so this is a sufficient condition, and of course now we're in the process of generalizing this to higher dimensions, and it's possible to have a similar statement in higher dimensions as well. Okay, so I've come to the end of my talk. Just a quick summary. So if you use a flow map as a hypothesis space, you can ask the same kind of questions that you always ask about a lot of supervised learning models. And here the optimization problem is really a mean field optimal control problem, and we can derive this kind of local necessary conditions in the form of maximum principle, which gives new algorithms and generalized backpropagation. And what I didn't talk about is also there are some interesting connections with the partial differential equations on the optimization end. And on the approximation end, we can come up with sufficient conditions for approximation using composition. So this really relies on the dynamics of the system, and repeated composition plays a central role in our results. Okay. Okay, so this is sort of what's different about, say, this approach to other kind of things that do not rely on this characterizing this concept. And of course, there's a lot of generalization aspects. The things in bold are things that I think are quick future work that needs to be done. Okay, so thanks very much. These are the references of the papers, and do you have any questions?
Yeah, maybe we still have one quick question.
So for this mean field theory method, is it possible to include interactions?
Good question. Yes. In fact, we have identified that one particular network structure with batch normalization. So if you consider batch normalization, this is true mean field dynamics in the sense that feed-forward dynamics not only depends on the states, but also depends on the distribution of the state. So this is really like a McKean-Vlasov kind of system. So batch normalization is an example of explicit mean field dynamics. Yeah. And I guess weight normalization and things like that are also of that kind.
Okay, because of time, I think we can resume more questions. So the next speaker today here is